Northern Arizona Territory, winter of 1881. While his neighbors raced to complete their standard plank cabins before the snow, former cavalry scout John M. was building something entirely different, something the other homesteaders had never seen before. His neighbors called it a tent house. They called him a fool. Why waste weeks on some strange contraption when a simple board and batten shack had worked for decades across the frontier? Then came the winter of 1885, 20 consecutive days below -10 degrees. Wind gusts reaching 60 miles per hour, the killing cold that would test every shelter on the mesa. Standard cabins failed. Interior temperatures plummeted to 15 degrees. Families burned 8 cords of wood in 6 weeks just to survive. But John's ridiculed brush shelter maintained 50 to 60 degrees while using only 5 cords. What did this former scout understand about surviving mountain winters that 2 generations of proven frontier wisdom had completely missed? The mesa country of Northern Arizona Territory drew settlers with promises that proved costly to believe. At 6,000 feet elevation, where ponderosa pines stretched toward thin mountain air, newcomers arrived throughout 1881 carrying Eastern building wisdom that had never faced this particular combination of altitude, wind, and cold. The territorial supply companies made it seem simple enough. Ship in pre-cut lumber from the railroad depot, hire local contractors who advertised cabin completion in 6 days, and trust the same board and batten construction that had housed families from Ohio to Kansas. Thomas R. represented this conventional approach perfectly. A farmer from Illinois, he arrived in late summer of 1881 and immediately contracted for a standard 12 by 16-foot shack. The design followed territorial building circulars to the letter: stud walls framed with 2x4 lumber, sheathed with 1.5-inch boards, and topped with a shallow-pitched roof to conserve materials. A single wood stove would sit centrally, just as it had in countless prairie homesteads. The entire structure cost him $230 in materials and labor, expensive, but the contractor promised it ready before the first snow. Trade stores throughout the territory promoted these specifications because they moved inventory efficiently. Board footage shipped easily by rail, standardized dimensions reduced cutting waste, and the familiar rectangular form required no specialized carpentry knowledge. Settlers appreciated the speed and predictability. Most importantly, the design had worked adequately in lower elevations and gentler climates, creating a false confidence that altitude and mountain weather patterns were merely variations on familiar themes. John M. watched his neighbors' construction methods with growing unease. His background provided a different lens through which to evaluate frontier building practices. 8 years as a cavalry scout had taught him to read landscapes for shelter potential, and his winters patrolling the Minnesota-Dakota border had demonstrated what happened when structure failed to match environment. Unlike most settlers, he possessed 2 distinct knowledge streams that challenged conventional territorial wisdom. His Scandinavian father-in-law had immigrated from Finland carrying generations of cold climate building experience. During long winter evenings in Minnesota, the old man had described techniques that seemed excessive by American standards. Log walls thick enough to resist frost penetration, earthen floors that stored daytime heat through bitter nights, and turf roofing systems that created insulation barriers 3 times thicker than standard American construction. These methods appeared labor-intensive and unfamiliar, but they represented survival knowledge tested across centuries of harsh Nordic winters. John's second knowledge source proved even more unconventional. His scouting duties had brought him into contact with Apache bands whose traditional dwellings challenged every assumption about proper frontier housing. Their dome-shaped brush shelters, called wickiups, used bent poles covered with thick layers of grass, bark, and brush to create surprisingly warm interior spaces. Apache families occupied these structures through mountain winters that killed unprepared travelers, yet the shelters appeared primitive and temporary to European eyes, trained on rectangular, permanent buildings. When John began clearing his homestead site in spring of 1882, his methodical approach immediately drew criticism from neighbors already settled into their board shacks. While others had rushed to complete standard construction, John spent weeks studying his 8-acre plot, observing wind patterns, tracking sun angles, and noting how snow accumulated in different micro-locations. His neighbors interpreted this deliberation as indecision or laziness. Thomas R. frequently commented that John would never finish a proper cabin before winter if he kept playing around with sticks and measurements. The social pressure intensified when John erected his first experimental structure. Adjacent to his main cabin site, he built what neighbors immediately dubbed a tent house or play camp, a small dome frame shelter using 8 poles set in a circle approximately 8 feet in diameter. The poles, each about 14 feet long, were bent inward and lashed together at the apex, creating a frame that looked nothing like proper frontier architecture. John then began covering this frame with brush layers, testing different thicknesses and materials as autumn temperatures dropped. His neighbors' mockery grew more pointed as winter approached. They called his brush covering Indian foolishness and suggested he was wasting time that should be spent on serious construction. Some wondered aloud whether Canadians and Scandinavians understood American building methods at all. The territorial building inspector, making his rounds in late autumn, noted John's unconventional approach in his report, but expressed confidence that the settler would come to his senses and build properly when the weather turned serious. John ignored the criticism and continued his experiments. His prototype shelter measured only 8 feet in diameter, deliberately small to test principles without committing excessive labor. He layered brush and grass to approximately 18 inches thick, anchoring the material with cord and wooden pins. During early autumn nights, when temperatures dropped into the 30s, he tested the shelter's heat retention by spending several hours inside with a small fire. The results encouraged him. The thick vegetal covering trapped warmth effectively, and the dome shape seemed to deflect wind better than flat surfaces. But John understood that his small prototype represented only the beginning of a larger challenge. The real test would come when sustained below-zero temperatures arrived, when fuel conservation became critical, and when structural integrity faced the full force of high-altitude winter conditions. His neighbors' confidence in conventional methods would soon meet an environment that had no patience for theoretical approaches that failed practical examination. The winter of 1882 arrived with unusual severity, testing every structure on the mesa within its first weeks. By December, Thomas R. discovered that his contractor had positioned his cabin with no consideration for prevailing wind patterns or solar exposure. The building sat squarely facing north, directly into the path of frigid air masses that swept down from the higher peaks. Worse, the shallow-pitched roof designed to conserve lumber costs began accumulating dangerous snow loads as storms deposited layer upon layer of heavy, wet snow that refused to slide off the gentle slope. On January 15th, after 24 inches of new snowfall in 3 days, Thomas heard the ominous creaking of roof timbers straining under weight they were never designed to bear. By morning, a section of his roof had sagged nearly 6 inches, allowing cold air to penetrate through gaps in the warped boards. The interior temperature at dawn registered 32 degrees Fahrenheit, while the exterior thermometer read 18 below zero, a difference of only 14 degrees despite burning wood continuously through the night. John witnessed this structural failure from his own homestead and understood immediately that his full-scale shelter required fundamentally different engineering principles. His small prototype had demonstrated the insulating potential of thick brush covering, but a permanent dwelling demanded solutions for snow load distribution, wind deflection, and thermal orientation that went far beyond simple brush thickness. The knowledge he needed came from an unexpected encounter in late spring. While tracking strayed horses near Oak Creek Canyon, John met an Apache elder named Yellow Bear, who was constructing a traditional wickiup for his family's seasonal camp. The old man worked with practiced efficiency, selecting 10 fresh oak poles approximately 14 feet in length and arranging them in a precise circle 12 feet in diameter. Unlike John's experimental prototype, Yellow Bear bent each pole carefully inward, lashing them together at the apex to create a dome framework 8 feet high at the center. Yellow Bear demonstrated how this dome shape served multiple structural purposes beyond simple aesthetics. The curved profile deflected wind around the structure rather than catching it like a flat wall, reducing both structural stress and heat loss through air infiltration. More importantly, the steep angles of the dome naturally shed snow and rain, preventing the dangerous accumulation that had compromised Thomas R.'s shallow roof. When John expressed interest in the construction method, Yellow Bear explained that his people had used this design for generations in mountain regions where heavy snows and fierce winds destroyed less appropriate shelters. John's second crucial knowledge source appeared during a summer expedition to the territorial capital. At a lumber camp north of Flagstaff, he encountered Eric N., a Finnish carpenter hired to build quarters for immigrant workers. Eric had grown up in the boreal forests of northern Scandinavia, where proper building orientation meant the difference between comfort and misery during 6-month winters. He described how Finnish builders always positioned their structures within 10 degrees of true south to capture maximum solar gain during the brief winter daylight hours. Eric explained the critical importance of site selection on sloped terrain. A south-facing slope of approximately 10 degrees provided optimal solar exposure while offering natural drainage for spring snowmelt. The gradient allowed low winter sun to penetrate deeply into the interior while preventing summer overheating when the sun tracked higher overhead. Eric had observed American settlers building without regard to compass direction, treating building sites as interchangeable plots rather than carefully selected positions that worked with natural energy flows. These conversations crystallized John's approach to his permanent shelter. He selected a south-facing location on his homestead with the exact 10-degree slope Eric had recommended. During late summer of 1882, he began clearing brush selectively, removing growth from the southern exposure to maximize solar access, while preserving juniper and oak shrubs on the northern side to create a natural windbreak against the prevailing cold air masses. John's construction incorporated Yellow Bear's dome framework scaled up to provide adequate living space for his family. He positioned 10 oak poles in a 12-foot diameter circle, bending each pole inward to meet at an apex 8 feet above the center point. The lashing technique required yucca fiber cordage, which he prepared by stripping and twisting the plant fibers until they formed strong, weather-resistant binding material. This dome frame provided the structural skeleton for a shelter that combined Apache engineering with Finnish site orientation principles. The most innovative element of John's design emerged from his analysis of seasonal solar angles. He constructed an overhanging eave lip extending 18 inches beyond the dome's circumference on the southern exposure. This overhang served dual seasonal functions. During winter months, when the sun tracked low across the southern sky, the overhang allowed solar radiation to penetrate deep into the interior, warming the space naturally. During summer months, when the sun climbed higher, the same overhang provided shade that prevented overheating while still allowing ventilation. When the winter of 1883 tested these design principles, the results validated John's synthesis of traditional knowledge. A blizzard in February deposited 30 inches of snow while generating wind gusts reaching 50 miles per hour. John's domed structure shed the snow load completely, with accumulation sliding off the curved surfaces rather than building up destructively. The wind deflected around the dome's profile instead of creating the direct pressure that had damaged neighboring rectangular cabins. Interior temperature measurements demonstrated the thermal advantages of proper orientation and structural design. On a February morning when the exterior temperature registered 7 degrees below zero, John's shelter maintained an interior temperature of 45 degrees Fahrenheit. His fuel consumption during a 5-week cold period totaled 4 cords of split wood, while Thomas R. burned 6 cords to achieve far less comfortable conditions in his conventional cabin. The dome structure had proven that traditional building knowledge, properly adapted to local conditions, outperformed conventional frontier construction methods that ignored fundamental principles of thermal dynamics. Structural engineering and environmental integration. The structural success of John's dome framework revealed a more fundamental challenge that winter weather would expose mercilessly. While his neighbors' plank cabins possessed solid frames, their building envelopes, the barrier between interior and exterior, consisted of single layers of 1.5-inch boards with minimal insulation. During a particularly brutal cold snap in early January of 1883, Thomas R. recorded interior wall temperatures that shocked him. When exterior conditions reached 8 degrees below zero, the interior surface of his cabin walls measured only 28 degrees Fahrenheit. Frost formed on the inside surfaces, Condensation created ice patches near the windows, and despite burning wood continuously, his living space never exceeded 20 degrees above freezing. John recognized that his dome framework, however well designed, required a completely different approach to thermal envelope construction. The solution emerged from his careful study of Yellow Bear's traditional techniques, combined with Eric N's Scandinavian cold climate experience. Yellow Bear had demonstrated the Apache method of layering brush and grass materials in thick, overlapping courses that created insulation barriers far exceeding anything used in conventional frontier construction. Working through late autumn of 1882, John began the painstaking process of covering his dome framework with vegetation gathered from his immediate surroundings. He collected yucca fibers, pine needles, oak leaves, and native grasses, sorting the materials by their insulation properties and durability. The covering process required systematic layering, beginning with coarse brush materials against the pole framework and progressing outward through increasingly fine materials that would shed moisture while trapping air. The final insulation thickness measured 36 inches, 3 full feet of layered organic material that created an envelope unlike anything his neighbors had ever seen. John secured each layer with cord lashings and wooden pins, ensuring that wind could not penetrate or displace the insulation. The completed covering transformed his dome into what appeared to be a large haystack, further amusing his neighbors who continued to question whether such construction could possibly function as serious shelter. But John's insulation system incorporated a second innovation that Eric N. had described from his Finnish homeland. Between the outer brush shell and an inner lining of half-inch boards, John maintained a consistent air gap of 6 inches. This double wall construction created a buffer zone that dramatically reduced conductive heat loss while providing space for air circulation that prevented moisture buildup and condensation problems that plagued single-wall cabins. The most sophisticated element of John's thermal system drew from both Apache and Scandinavian traditions: a thermal mass bench that would store heat during the day and release it steadily through cold nights. Around the interior perimeter of his dome, John constructed a raised bench 18 inches high and 12 inches thick, built from earth, clay, and carefully selected stones. This bench occupied approximately 10 feet of the dome's circumference, creating both seating and sleeping space while serving as a massive heat storage system. The bench construction required specific knowledge about thermal mass materials that John had learned from both his cultural sources. Yellow Bear had explained how Apache families used heated stones and earth floors to extend warmth through mountain nights when fires burned low. Eric N. had described similar thermal mass systems in Finnish saunas and winter dwellings, where stone and earth benches absorbed heat from wood fires and radiated it for hours after the flames died down. John's bench system integrated directly with his heating strategy. Each evening, he built a fire in his centrally located wood stove, allowing the heated air to warm the earth and stone bench throughout the interior. The thermal mass absorbed this heat energy and continued radiating it long after the fire subsided, maintaining comfortable interior temperatures without requiring continuous fuel consumption through the night. The first serious test of this integrated insulation and thermal mass system came during a sustained cold period in February of 1883. For 6 consecutive nights, exterior temperatures remained at or below 10 degrees below zero, with 2 nights reaching 15 below. John's shelter maintained interior temperatures between 60 and 65 degrees. Fahrenheit measured at dawn, a differential of 75 to 80 degrees from exterior conditions. More significantly, his fuel consumption during this cold period totaled only 3 cords of wood over 5 weeks, while Thomas R. burned 6 cords during the same period to achieve interior temperatures that barely reached freezing. John's thermal mass bench remained warm to the touch each morning, indicating that the heat storage system was functioning exactly as traditional knowledge had predicted. The performance difference became even more dramatic during windstorms that tested the envelope systems directly. When 40-mile-per-hour winds struck the mesa in March, Thomas R.'s cabin became almost uninhabitable as cold air infiltrated through gaps between boards and around windows and doors. His interior temperature dropped to 20 degrees Fahrenheit despite a roaring fire in his stove. Meanwhile, John's thick insulation envelope and air gap system prevented wind infiltration entirely, maintaining steady interior conditions regardless of exterior weather violence. John documented these results meticulously, understanding that his synthesis of traditional techniques was producing measurable performance advantages that challenged fundamental assumptions about frontier construction. His neighbors could no longer dismiss his methods as primitive experiments when the evidence demonstrated superior comfort, dramatically reduced fuel requirements, and structural integrity that exceeded conventional building practices. The integrated system, dome framework with thick vegetal insulation, double wall construction, and thermal mass benching represented a complete departure from territorial building wisdom. Yet every component drew from proven traditional knowledge that had sustained human survival in harsh climates for generations. John had simply recognized that frontier conditions demanded frontier solutions rather than imported assumptions about appropriate construction methods. By spring of 1883, other homesteaders began visiting John's shelter to observe its construction details and thermal performance firsthand. The superior thermal envelope John had created revealed a new challenge that conventional frontier heating could not address effectively. Standard cabin arrangements placed a single wood stove centrally and relied on radiant heat to warm the entire space. But this approach created dramatic temperature variations that wasted fuel while leaving occupants uncomfortable. Thomas R.'s cabin demonstrated this problem clearly during the winter of 1883. The area immediately surrounding his stove reached uncomfortably high temperatures, often exceeding 80 degrees Fahrenheit, while corners and sleeping areas remained 30 to 40 degrees cooler, forcing his family to cluster near the stove or burn excessive amounts of wood trying to heat the entire space uniformly. John understood that his integrated shelter system required equally sophisticated heating and air circulation methods. The solution emerged from his conversations with Eric N., who described heating systems used in Finnish saunas and winter dwellings that distributed warmth evenly rather than creating hotspots and cold zones. The key principle involved using the thermal mass bench not merely as a heat storage system, but as an active heat distribution network that could warm the entire interior space efficiently. Working through the autumn of 1883, John excavated a series of narrow channels beneath his thermal mass bench, creating an underground air circulation system that connected to his centrally placed wood stove. These channels, approximately 6 inches wide and 4 inches deep, ran beneath the entire length of his bench system, allowing heated air from the stove to travel through the thermal mass before entering the living space. The channels were lined with flat stones to prevent collapse and covered with earth to maintain the bench's structural integrity. This heat exchange system functioned through controlled air movement that Eric N. had observed in traditional Scandinavian construction. John installed a dedicated fresh air intake near floor level on the south side of his dome, a 6-inch diameter opening fitted with an adjustable wooden shutter that allowed him to control airflow volume. Cool exterior air entered through this intake, traveled through the heated channels beneath the bench, where it warmed significantly, then rose naturally into the living space through small openings along the bench's inner edge. The circulation system required a corresponding exhaust mechanism to function properly. At the apex of his dome, John installed a smoke flue that served dual purposes. It exhausted smoke from his wood stove and provided an outlet for the warmed air that had completed its circulation through the interior space. This created a continuous convection current that drew fresh air in from the bottom, warmed it through contact with the heated thermal mass, circulated it through the living space, and exhausted it at the top, maintaining steady air exchange without losing excessive heat. The system's effectiveness became apparent during John's first winter of operation. While Thomas R.'s cabin exhibited temperature variations of 40 degrees between stove area and sleeping corners, John's shelter maintained temperature differences of less than 10 degrees throughout the interior space. The heated air circulation ensured that every area received consistent warming, eliminating the cold zones that plagued conventional cabins and reducing the fuel required to achieve comfortable conditions throughout the entire living space. But John's most innovative breakthrough addressed a problem that conventional cabins could not solve: seasonal adaptability. Summer conditions in the Arizona Territory created interior temperatures that made standard cabins nearly uninhabitable. During July of 1884, Thomas R's cabin reached interior temperatures of 95 degrees Fahrenheit, while exterior conditions measured only 80 degrees. The same insulation and structural features that provided winter comfort became heat traps during hot weather, with no effective method for cooling or ventilation. John had anticipated this seasonal challenge during his original design process. Yellow Bear had demonstrated how Apache families modified their wickiups seasonally, removing outer covering layers during hot weather to allow air circulation while maintaining structural integrity. John incorporated this principle into his brush shell system, designing the outer insulation layers so that approximately one-third of the covering, primarily on the south-facing exposure, could be removed and stored during summer months. This seasonal modification transformed his shelter's thermal characteristics completely. Removing the thick brush layers on the south side created ventilation openings that allowed hot air to escape, while drawing cooler air through the controlled intake system. The remaining insulation on the north and west sides provided shade and protection from afternoon sun, while permitting air circulation that prevented heat buildup. John also recognized that his thermal mass bench, so beneficial during winter, would become a liability during hot weather if left uncovered. Drawing from Apache seasonal practices, he covered the bench with woven mats and blankets during summer months, insulating it from interior air temperatures and preventing it from absorbing and radiating unwanted heat. This simple modification allowed the bench to remain neutral rather than contributing to interior heat gain. The summer of 1884 provided the definitive test of this seasonal adaptability system. When exterior temperatures reached 90 degrees Fahrenheit, John's modified shelter maintained interior temperatures of 72 degrees, while Thomas R's cabin became virtually uninhabitable at 95 degrees. The controlled ventilation system drew cool morning air through the structure and exhausted heated air through the apex opening, creating continuous air movement that provided natural cooling without requiring any mechanical systems. John's fuel consumption during this period dropped to minimal levels. He used his wood stove only for cooking and occasional evening warmth during unexpectedly cool nights. The ventilation system functioned entirely through natural convection, requiring no additional energy input while maintaining comfortable conditions that allowed normal daily activities throughout even the hottest summer weather. By autumn of 1884, several neighboring homesteaders had observed John's shelter performing effectively through both winter and summer extremes. Samuel D., a settler who had arrived the previous spring, spent considerable time studying John's heating and ventilation systems, taking careful notes about the air channel construction, intake and exhaust placement, and seasonal modification techniques. The integrated approach, combining structural design, thermal mass, controlled air circulation, and seasonal adaptability, represented a complete departure from conventional frontier building that addressed environmental challenges conventional methods simply could not handle. The winter of 1885 arrived with unprecedented severity that would test every shelter system on the mesa beyond anything previously experienced. Beginning in late November, a series of Arctic air masses descended from Canada, bringing sustained temperatures that remained below -10 degrees Fahrenheit for 20 consecutive days. Wind gusts reached 60 miles per hour, creating conditions that penetrated every weakness in conventional construction. Most critically for isolated homesteaders, heavy snowfall accumulated to depths exceeding 3 feet and remained on the ground for over a week, cutting off the supply route from the territorial capital and leaving families dependent entirely on their stored resources and fuel reserves. Thomas R's cabin, along with 3 other conventional structures in the immediate area, began failing catastrophically within the first week of extreme conditions. The shallow-pitched roofs that had suffered damage in previous winters could not handle the sustained snow loading. Ice dams formed along the eaves, forcing meltwater back under the shingles and into the living spaces. Thomas R. recorded interior temperatures dropping to 15 degrees Fahrenheit at dawn, despite burning wood continuously throughout each night. Frost formed thick layers on interior walls, and water stored in open containers froze solid even when placed near the wood stove. The fuel consumption required to maintain barely survivable conditions quickly exhausted stored wood supplies. Thomas R. and his neighbors burned 8 cords of wood during the 6-week crisis period. forcing them to burn furniture, fence posts, and eventually structural elements from outbuildings to maintain fires. Two families abandoned their cabins entirely and moved to temporary quarters in town, unable to keep their shelters warm enough for human habitation. John's integrated shelter system faced the same brutal conditions, but responded with remarkable stability. His dome structure shed the heavy snow loads without stress. The thick insulation envelope maintained thermal barriers that conventional construction could not match, and his heating circulation system distributed warmth efficiently throughout the interior space. Most significantly, his shelter demonstrated capabilities that extended far beyond simple temperature control. The thick-walled thermal envelope created interior conditions that allowed normal food storage and preservation throughout the crisis, while conventional cabins suffered freezing temperatures that spoiled stored potatoes, preserved meats, and other essential supplies. John's shelter maintained interior temperatures consistently between 50 and 60 degrees Fahrenheit measured at dawn. His family's food stores remained perfectly preserved, and water containers never approached freezing despite the extreme exterior conditions. John's fuel consumption during the 6-week emergency totaled only 5 cords of wood, a significant savings compared to his neighbor's 8 cords. But more importantly, this reduced consumption meant he never faced the desperate fuel shortages that forced other families to burn irreplaceable possessions or abandon their homes entirely. His heating system's efficiency allowed him to maintain adequate warmth while preserving sufficient fuel reserves to continue normal operations throughout the entire crisis period. The performance differential became so dramatic that it attracted official attention from territorial authorities. Edward M., the county building inspector who had previously noted John's unconventional methods with skepticism, arrived in late January to investigate reports of a shelter functioning normally while conventional structures failed around it. Edward M. documented interior temperatures, examined the structural integrity after sustained snow and wind loading, and measured the fuel consumption rates that seemed impossible by conventional standards. Edward M.'s inspection revealed technical principles that challenged fundamental assumptions about appropriate frontier construction. The dome framework had not only survived without structural damage, but showed no signs of stress or deterioration. The insulation system had maintained its integrity and effectiveness despite weeks of extreme weather. The heating and ventilation systems continued operating efficiently, providing consistent interior climate control that exceeded the performance of much more expensive conventional construction. Most significantly for the future of frontier building practices, Edward M. observed that John's methods could be replicated using locally available materials and traditional construction skills. The techniques required no specialized tools, imported materials, or advanced technical knowledge beyond careful observation of natural principles and traditional building wisdom. Any homesteader with basic carpentry abilities could construct a similar shelter using resources available throughout the territorial pine country. Samuel D., who had been studying John's methods since the previous summer, began construction of his own brush dome shelter during the spring of 1886. Working with John's guidance, Samuel D. successfully implemented the integrated system, dome framework, thick vegetal insulation, thermal mass bench, and controlled ventilation, proving that the techniques could transfer effectively to other builders and locations. Word of the shelter's performance spread through territorial building networks during 1886. The Mining Camp Building Journal published Edward M.'s inspection report in its spring edition, describing John's methods as unorthodox but remarkably effective, and recommending investigation of traditional building techniques that might offer advantages over conventional frontier construction. This official recognition legitimized approaches that had previously been dismissed as primitive or impractical. By 1890, homesteaders throughout the Pine Mesa region had begun adopting elements of John's integrated system. Some built complete brush dome shelters following his exact specifications, while others incorporated specific techniques, thick vegetal insulation, thermal mass benching, or controlled ventilation systems, into more conventional rectangular structures. The Territorial Extension Service began referencing brush chamber insulation methods in their building circulars, acknowledging that indigenous and immigrant traditional knowledge offered practical advantages over standard American frontier construction. The long-term legacy extended far beyond the immediate region. Survival manuals produced in the early 20th century included descriptions of brush dome emergency shelters suitable for high altitude Western conditions. Modern analysis of log home failures in mountain regions consistently identifies inadequate roof pitch for snow loading and insufficient insulation as primary causes of structural problems, the same issues that John's traditional knowledge synthesis had addressed over a century earlier. John's achievement demonstrated that frontier survival depended not on rejecting traditional knowledge in favor of modern methods, but on carefully selecting and combining proven techniques from multiple cultural sources to address specific environmental challenges. His success validated the principle that effective building practices emerge from understanding natural systems rather than imposing theoretical solutions that ignore local conditions and climate realities.